Let's ask this question: what are irrational numbers? Before answering this question, let's try to ask what are rational numbers? Well, these are the numbers of the type p by q, where p and q are integers and q is not equal to 0. Example 1 by 2. It is of the type p by q and both are integers. 1 and 2 are integers. Another example 3 by 4. It is of the type 3 by 4 and so on. We have minus 7 by 9. Wow, we have 8 by 3 and also 20. That's also a rational number because it can be written as 20 divided by 1, and 20 is an integer and 1 is also an integer. Then what should be irrational? Well, these are not numbers that are not rational and also that have decimal expansion. They have decimal expansion. These are numbers that are not rational and they have decimal expansion. Okay, what do we mean by these numbers that have decimal expansion and they are not rational? Let's look at the rational numbers once again. We have a few examples like 1 by 2 and 3 by 4. 1 by 2. That can be written as 0.5 and 3 by 4. If you divide 3 by 4, then you get 0.75. Oh, they have decimal expansion. Okay. So what are those numbers? Once again, irrational are numbers that are not rational. That means they don't have, they can be written in the form p by q, but they have decimal expansion. Well, to answer this, let's look at the history. We have a right angle triangle. Let this be hypotenuse. We can write hypotenuse by h. Let this be p. Let this be b. Then, by Pythagoras Theorem, we know that h square equal to p square plus b square. So this was the theorem discovered by Pythagoras. However, let's try to compute the length of a hypotenuse of a right angle triangle whose base is 1 unit and perpendicular is also 1 unit. Then we have h square equal to, once again hypotenuse is h square is 1 square plus 1 square. And so h square equal to 2. So what do you think hypotenuse should be? It should be a number h so that h square equal to 2. Now, Pythagoreans did not know what were irrational numbers. So they tried to determine, must have tried to determine, what is that number h so that h equal to 2. So maybe h equal to, maybe it's just equal to 1.4. So let's try it. So that is equal to, let's say, 14 by 10. If we take h equal to 1.4, that's not exact value but roughly, then h square will come out to be, if you multiply 1.4 by 1.4, you get 1.4 into 1.4 equal to 1.9. 1.96. So h squared is 1.96. That's almost equal to 2, because if you subtract, let's try to find the error. If we take h equal to 1.4, then what is the error in h squared? Actual value is 2, minus we have observed value is 1.96, and that is 0.04. Yeah, that's almost 2. Okay, maybe somewhere equal to 1.4. Then they must have said, well, it is more accurately equal to 1.414. Let's see what happens then. If we write h equal to 1.414, then h square will turn out to be 1.414 into 1.414. 4 into 4 is 16, 4 into 1 is 4, 4 plus 1 is 5, 4 into 4 is 16, 4 into 1 is 4, and plus 1 is 5. Again, 1 into 4 is 4, 1 into 1 is 1, 1 into 4 is 4, 1 into 1 is 1. 4 into 4 is 16, 4 into 1 is 4, 4 plus 1 is 5, 4 into 4 is 16, 4 plus into 1 is 4, 4 plus 1 is 5, and lastly 1 into 4 is 4, 1 into 1 is 1, 1 into 4 is 4, 1 into 1 is 1. 6, 9, 6 plus 6 is 12, 12 plus 1 is 13, carry over 1, 4 plus 5 is 9, 9 plus 9 is 18, 18 plus 1 is 19, carry over 1, 6 plus 2 is 8, 8 plus 1 is 9, 4 plus 5 is 9, and 1. We have got 6 number of decimals, 1, 2, 3, 4, 5, 6. So if you take h equal to roughly 1.44, then h square will turn out to be 1.999396. Again, let's determine the error this time. If you subtract 1.999 this from 2, then you get 4, 0, 6, 0, 0, 0 point. Wow, we are getting much accurate value of h, but not perfect value. Well, Pythagoreans must have tried this, and they were never able to get exact decimal expansion of root 2. So, they must have guessed maybe there's something wrong here. So, let's write root 2 equal to p by q. We want to find out exactly what is that p and q, because we are so far we are just computing trying. We are getting better and better value of p and q, but not the perfect one. So let root 2 equal to p by q, comma p comma q are integers, and they have no common factor. P and q have no common factor. No common factor. Alright, then what can we say? Then, if we square it both sides, then 2 equal to p p square by q square. And then 2 into q equal to p square by q. We observe that q is an integer, so 2 into q is an integer. This is just an integer. Whereas p square by q, this is not an integer. Hey, we have a problem. Left hand side we are saying 2 into q is an integer, and right hand side we are saying p square by q. Obviously q cannot be equal to 1 because no integer is square equal to 2. If you take q equal to 1, then you will get 2 equal to p square. That's not true. Then 2 into q left hand side is an integer, while right hand side is not an integer. Two numbers are equal, one of them is integer, others is not an integer. Obviously, if you write that kind of thing, then teacher will say, well, teacher will say, you made a mistake here. Where did you make a mistake? Well, we made a mistake because we have started with root 2 equal to p by q. P comma q are integers. So if we start with such a thing like root 2 equal to p by q, where p and q are integers, then we will come to the conclusion that, well, we have made a mistake once again. Then what can we do? We can't start with saying that root 2 equal to p by q, where p and q are integers. So we can say root 2 is never expressible is integer divided by integer. So we are able to get a number which is never expressible as integer divided by an integer. Okay, grammatical mistake. Integer divided by an integer. Alright, so we have actually produced an irrational number. What are irrational numbers? Those numbers that cannot be expressed in the form integer divided by an integer. Now, root 2 is not just the only irrational number. There are other irrational numbers like square root 3, square root 5, you may say square root 9, but that's not correct because square root 9 is 3 and 3 is 3 by 1, so it is integer by integer. So root 3, root 5, and something called pi, that is the ratio of circumference divided by diameter of a circle, and other numbers. There are in fact infinitely many of them, but we have just produced a few of them.